Okay, so welcome everyone for this new SIPTA seminar of the month of April. So in a few moments, I will hand over the mic to Michele to present to us our speaker of today, which is Krikamol Muandet from SISPA, from Saarbrücken. And he will talk to us about a mix of imprecision and machine learning. A very interesting topic, very timely as well.
Yes, thank you very much, Sebastian. Hello, everyone. I'm very happy to be here to chair this session. Krik and I became friendly and friends a few months ago. Krik is a PI at CISPA, and he's also an Ellis scholar. That, for those of you who are not familiar with what Ellis means, so Ellis is the European sovereign thing for machine learning and AI, and you need to be elected as a member to be at Ellis. And then once you're a member, you can go one step up, which is being an Ellis scholar or an Ellis fellow, depending on the level of seniority. And Krik is an Ellis scholar, so a very a star in the field. He likes to do research in modern kernel machines, causality, and algorithmic decision making. And I want to take a couple of minutes just to tell you how we got into contact with one another. So Krik wrote a very nice paper on domain generalization using imprecise techniques, which is how I came to know him. And funnily enough, in the same time I wrote a paper on statistical learning theory using Krill techniques whose mechanisms were pretty similar to the one that he used for his paper. And so we got in touch, and after a while he invited me to visit him in Saarbrücken, and it was a very nice week when I was there. And likewise, I invited a student of a postdoc of his to visit me in Manchester. So it was like a nice combination. And so all of this to say that the imprecise probabilities are not only intellectual fulfilling, but also relationship-wise, they are they convey nice meetings. So without further ado, Krik, the floor is yours. Thank you very much for being here.
So thank you very much, Michele, for a very kind introduction. I want to say that I'm actually a big fan of this seminar series. I think if you notice, I've been at a seminar almost all seminar, because I really enjoy this. And now it's actually even better to be able to speak at this seminar. So thank you so much for the organizer for inviting me here. So I'm basically coming from machine learning communities, right? And then as Michele already introduced, right, I think one of my sort of research topics that actually very close to my heart is the question of generalization, right? And I've been thinking about this problem for many years since I started my PhD, and I have a feeling that the community is missing something, right? And I believe that imprecise probability is one of the missing piece for us to be able to answer, like how to build intelligent system or machine learning system that can truly generalize, right, to unseen environment, right? And for this, I want to start by giving sort of telling you a bit about my inspiration. So back in 2011, when I started my PhD, I had the opportunity to actually co-organize a symposium in honor of the 75th birthday of Vladimir Vapnik, who is basically the sort of the father of statistical machine learning, and basically who laid the foundation of what we know today as statistical machine learning, right? And also sort of help us so he sort of helped us sort of understand how to build an intelligent system that can truly generalize, right? And I want to say sorry to Bob Williamson, because I had a picture with Bob Williamson in that in this as well, but I couldn't find the original copy, so I'm sorry for that. But also Bob was there when we organized this symposium. So I think through the interaction with Vladimir Vapnik and many people at this symposium that actually helped me a lot in terms of understanding about how we can actually build a truly intelligent system. So what is generalization, right? So I think when we talk about generalization, the first thing that I think about, or at least come up to my mind, is like this example. Let's say if I give you a sequence of number, right? A sequence of observation, right? And then basically I ask you to make a prediction about the next number, right? I think for this sequence, it's probably going to be very easy for everyone to figure out, right? Because basically what's going on in our mind is basically we start by, okay, right, forming a sort of a model of how the data could have been generated, right? So in this case, I generate the data using this formula, 2x, right? And then where x represent the position of this number. So basically the next number would be 22, right? Okay, now what if I give you this sequence instead, right? So now I think some of you might wonder, okay, this look a bit more complicated. Is there any actually pattern to this, right? Maybe I will give you sort of a few seconds to figure out what would be the model for this sequence. Right. So I think for many people, I think you might come up with different sort of model that could help predict the next number, right, in this sequence. But it's actually the same rule that I used to generate the first sequence. The only difference is basically I add random noise to the sequence, right? So to make it harder to sort of detect any pattern in the sequence, right? And this is actually what happened in the real world, right? Whenever we observe something, there's going to be some sort of uncertainty in the sequence, right? And then for us, right, at least for human, right, we have an ability to at least distinguish pattern from just noise, right? And in this case, basically, whenever we make prediction, we're gonna always suffer from some sort of error in the prediction as well, right? But how is this example going to be useful, or why is this generalization is going to be useful? But essentially, this is actually the same principle that we use in building large language model, right? We use network prediction. Right? We look at the corpus of available text and then use that to train a model that help us predict what would be the most likely word in the sentence. It's also the same principle that we use in building autonomous driving, right? We use it to sort of detect which object is the car, which object is a person, or which object is the traffic light. It's the same principle that we use in scientific discovery with AI, right? We look at a sequence of protein that we already know the property of, and then we try to build a model of that and then generate a new pattern that we never observed before, right? So this is a very simple idea, but lead to many powerful application, right? And now the question is actually, how should we formulate this kind of learning problem, right? So that we can use computer, right, to sort of detect pattern in the data, right? And one of the early algorithm or the early principle, right, that allow us to actually formulate this kind of problem in a systematic way is called empirical risk minimization, basically proposed by Vladimir Wapnick. So the way that he think about it is that basically what we have is a sample, let's say of psi n from some fixed but unknown probability distribution. And let's say this probability distribution is a joint distribution between x and y, right? So x here represent the input, right? And y represent the output that we are interested in. For example, x could be images, and y could be maybe the label that we assign to different objects in the image, in the case of a self-driving car. Right? And these observations or these samples are drawn IID from this probability distribution. Right? And the goal is basically we want to find the best hypothesis, right, from some hypothesis class of basically function from X to Y. Right? And the recipe of EIM is basically just basically minimize an empirical error on the observed data. Right? And this can be formulated as you can see on the slide, right? We just basically find the best hypothesis by minimizing the average, right, loss, right, that the hypothesis made on the observed data, right? And why is this a good idea, right? This is a good idea because we know that as n go to infinity, right, these quantities, right, the empirical risk will convert to what we call the expected risk or population risk, right? And this kind of gives us sort of the guarantee that if we sort of deploy this empirical solution, the performance should get better and better in comparison to the population solution. And in this case, we assume that S star, which is the best hypothesis, belong to the hypothesis class. So, right. And typically, right, in this case, we deal with the uncertainty that we see from the data by sort of getting the generalization bound, right? So in this case, we're trying to bound the difference between the true risk of the empirical solution and the true risk of the best solution in the hypothesis class, right? And this kind of bound is useful in the sense that now we get the idea of how fast, right, this error decay to zero, right? And one thing we should note here is that we have this bound is because we need to deal with what I would call data uncertainty, right? Data uncertainty is basically the uncertainty that comes from the fact that the learner have just a finite data, right? Finite observation of the data. But then this uncertainty basically will decay as we observe more and more sample, right? So the way that I think about this is actually that we have a learner, right, that try to learn from the observed data and the best hypothesis in the hypothesis class. And the IID assumption, right, the way I interpret this is that we have a learner who would calibrate their belief probability to the physical probabilities. And this physical probability is the probability that actually generated the data, right? And then look, by using this interpretation, we can kind of trying to understand EIM from an expected utility theory of von Neumann or Morgenstern, right? And under some sort of rationality axiom, we can say that, okay, this learner kind of assumed that there's some underlying physical property, and then he believed that this is the right physical property probability. Then the sort of the most rational way of this agent to do is basically to minimize the expected risk, right? So I want to point out that given this formulation, right, the focus of machine learning research in the past 10 to 20 years is basically on coming up with a powerful hypothesis space. For example, kernel method, right? Kernel method use reproducing kernel Hilbert space. In deep learning community, there's so many architecture, for example, CNN or transformer. Also, there's a lot of focus on, designing efficient optimization algorithms such as SGD to solve this optimization problem. Last but not least, also there's a lot of investment in scalable data and compute, right? Such as MapReduce or GPU and TPU, right? And so the way that I understand EIM is basically as precise learning. What I call precise learning. So what I mean by precise learning is basically we have a learner who represent his belief about the data generating process by a single precise probabilities, right? Let's put it that way, right? And then based on that belief, sort of trying to act by choosing the best hypothesis from the hypothesis space by minimizing the expected risk, right? Now, one of the key limitations of ERM, of course, is that the IID assumption will always be violated in the real world, right? In the real world, basically, the training data and test data may not be independent and identically distributed, right? One of the very good example is basically when you have data that come from, let's say, one hospital in the cities, and then because this hospital has a lot of money, right, they can collect data and then train machine learning models. But then when you try to deploy that model, let's say in a hospital, in a more rural area, right? The data that they collect may have different type of quality or different sort of characteristic to the data that the model observed during training. So in that case, the test distribution and training distribution is going to be different, right? And it's the same with, let's say, autonomous driving or self-driving car, right? So the car may be the company that built self-driving car, right? Train the autonomous car in the cities, right? Where the company is located. And then when actually the company wanted to deploy this autonomous car to different country, right? They're gonna be basically observe different kind of data. So they're gonna be some sort of distribution shift, right? That come basically from this kind of environment changes, right? The changes in the environment, right? So basically, when the IID assumption is violated, right? So now suddenly we have to deal with the additional source of uncertainty, right? So before we only deal with data uncertainty, right? It's the uncertainty that the learner have because of the finite number of data, right? Now, because of the uncertainty in the actual data training process, right? The distribution shift. So now we have the uncertainty that we call distribution uncertainty, right? The learner itself is uncertain about the data distribution, right? So now the question in this line of research is basically how to design a learning algorithm, right? In such a way that you can still learn from the training data and then generalize to the test data that may come from a different distribution than the training distribution, right? And this is commonly known as out of distribution generalization or OOD generalization for short, right? And I think the point of this talk, the key message that I want to make here is that I want to emphasize that existing work, right, deal with the distribution uncertainty, but they try to reduce the problem into precise learning, right? They still deal with the non-IID-ness of the data, but then the approach they use is that they didn't account it for the imprecision that arise from this distribution uncertainty. And then basically I'm going to talk about how we actually can overcome this limitation. Right. So the first, I think, line of work that deal with this problem is called domain adaptation, right? In domain adaptation, you assume that the training data, right, come from a different distribution than the test distribution. Let's say the training distribution is P, and then the test distribution is Q, right? So ultimately, right, if we know Q, or if we have access to the sample from Q, we can just formulate the problem as an ERM, or expected risk minimization, right? And then we can minimize this objective instead, right? But ultimately, we don't want to do that because I think that's not the problem we're trying to solve, right? The problem we're trying to solve is that we only have access to the training data, and then we somehow want to use the training data and maybe some information about the test data to build a model, right? But we can observe that actually we can rewrite the expected loss under Q as expected loss under P. But this also depends on the density ratio between Q and P, right? So now we can actually learn the best hypothesis from just training sample if we have access to this. Unfortunately, we also don't have access to this, right, in the real world, because if you have access to data from the test distribution, then we can just use that, right? And this is still, I think, precise learning, because now you actually treat the distribution uncertainty by basically reviewing some information about the test distribution. And now the precise learner is going to represent that uncertainty by a precise distribution, which is Q, right, in this case, right? So to kind of resolve this problem, I think one line of research is basically one of the most studied, I think, research area in machine learning is called covariance, right? In covariance, you basically assume that the only thing that changes between training distribution and test distribution is the marginal distribution, right? And now the conditional distribution of y given x remain the same between training and test domain, right? And for that, we can then now reduce this formulation, right? We can write the density ratio now in terms of just the marginal of Q and P, right? And this density ratio now is estimable from unlabeled data alone from the test distribution. So in this setting, we have labeled data from the training domain, but we have some unlabeled data from the test domain. So that's not unrealistic to assume that basically in the test domain, you have some unlabeled data, right? And then you want to sort of use that data to correct for a bias introduced by this distribution chip. And this, of course, relies on the assumption that P is absolutely continuous with respect to Q, right? So this is one example, but actually there exists a bunch of settings that people look at in the literature. For example, you can also look at label chip, conditional chip, concept chip, and confounding chip, for example, right? Now, but I think the overall sort of idea in this line of research is that you still have precise learner, right? You still have precise learner that represent their belief by just a single precise probability distribution. In this case, it's Q, right? And by making some simplifying assumption about how the data are generated, this learner can estimate, right, the expected risk under Q in one way or another, right? And so the key assumption, right, that people make in domain adaptation or covariance chip is that we observe some data from the test distribution, right? Now, the question is, what if we don't observe any data from the test domain, right? So in that setting, I think the setting that people also study a lot, right, in the communities is this setting of domain generalization, right? And these are basically the first two papers that look at this problem. And the term domain generalization is actually coming from our work, right? So this is now become a common term that people use in the field. So the idea of domain generalization is, you only have access to training data, right? You never actually observe any data from the test domain, right? But you assume that you have a collection of training distribution, right? You can observe data from multiple domains. For example, this domain could represent, maybe you have data from multiple hospitals across Germany or across different countries, right? And then you want to basically use that data, right, to train a model that would work well in the previous, in the unseen domain, right? So you want to, let's say you want to collect data, right, from, let's say, 10,000 hospitals in Germany. and train a model, and then you want to deploy that model to a different hospital, let's say in a different country or even in Germany, right? Now the question is how can we do that, right? I think this become even more difficult, right, than just domain adaptation, because now we don't know anything about the test domain. So it means that we have to sort of make some assumption about like the relationship, right, between the training domain and test domain, right? So basically the way that we formulate this problem, at least back in 2013, is that we assume that there exists what we call a meta distribution, right? A meta distribution that generate training domain, right? Is basically generate a joint distribution between X and Y, right? And among these training domain, we're gonna observe some finite training data, right? And then we're gonna assume that the unseen test data come from another distribution that has been generated by the same meta distribution, right? So I think back then, I don't have any sort of knowledge about imprecise probabilities. So the way, I think this comes as a natural choice for us, but I think thinking back, I think in the language of imprecise probability, this is a different way that you would use to represent this a second order uncertainty, right? I think you call it a second order probability distribution, right? And that's basically the way that we formulate it. But I think right now, after looking at the imprecise probability literature, I think maybe a better way of representing this kind of uncertainty is through Credo set, right? And I hope everyone have already know about Credo set, but basically the Credo set is basically just a closed convex set of probability distribution. And in this talk, I would basically mostly talk about the Credo set that is finally generated by the training distribution that I observed. Okay. And in our work in 2013, right? Our goal is basically to learn this hypothesis. And this hypothesis is different from the hypothesis that we have seen before, because now this hypothesis also takes some information about the marginal distribution of X, right? When you make prediction. And this comes from the fact that during test time, right? Sorry. During test time, we also observed that we have some access to unseen test data, a collection of data. So we can somehow infer that information about the marginal distribution of X and then use that in the prediction as well, right? So that's the idea, with the hope that, by giving the model this information, we can make better prediction about the new instant X, right? Okay, so the idea that we proposed back then in 2013 is this invariance principle, right? So when you observe a bunch of training domain, let's say you have observed a different data set from, let's say, different hospital, right? So the idea is that we have to be able to generalize, we have to assume something about what remain invariance across these domains, right? And I call that invariant principle, right? And in this paper, we propose to learn a feature representation phi, right? This is a feature representation of X that try to satisfy these two criteria. The first one is that it should minimize the distributional variance of the marginal distribution of X, of phi of X. This means that basically this representation should make the marginal distribution across the domain look the same, right? That's what it basically means. And at the same time, it should also preserve the functional relationship between the representation and Y, right? And So we propose this domain invariant component analysis, or DCAR, that basically does exactly this. So we find a representation file, right, that preserve central subspace. So central subspace here is a technique that basically tell us that the subspace that we learn is going to preserve functional relationship between X and Y. And then we want the distributional variance to be small, right? And in this work, we use kernel mean embedding to represent probability distribution. And what we're trying to do is we're trying to minimize the variance of the kernel mean embedding in the Hilbert space, right? So that, you know, the representation that we get kind of cannot distinguish between different marginal distribution. And then at the same time, also try to preserve the functional relationship between this. And if you are interested in learning more about kernel mean embedding, we have this book, which is also available online. So if you're interested, please check it out, right? Okay, so I think that's the idea. And so these are the result of applying different feature representation learning to the data that we generate across different domains. So here you can see this one, right? The first plot is the data that we projected onto kernel PCA component. And it's the same here, but with different techniques, right? The first one is from the training domain, right? This is from the training domain. And all the remaining are from the test domain, right? These are all from the test domain. This is as well, right? So basically, the ideal situation for us is that the data should look the same across domain, right? After the projection, we want the data to look the same so that, you know, it's easier to generalize to the new domain, right? And if you look at kernel PCA, you can see that it's kind of look different, right? Also, this one also, well, not this one, because this one is our proposed method, but this one look different. This one kind of looks similar, but it's different from the training domain, right? And this one is what we propose. So here we can see that the marginal distribution also look kind of similar. And at the same time, the functional relationship represented by the color also preserved, right, in this projection. Right? And this sort of the idea of why we can actually learn to generalize better after we learn this feature representation, because we kind of do transformation in such a way that the data look like an IID data, you know. And then when the test data come, we just do this projection and then apply this the standard learning algorithm on that data. Right? So after learning this representation, we basically just minimize the average accuracy across domain, right? And we have this also we prove the generalization, well, the learning theoretic bound, right, on this using the average accuracy. And basically we show that this distributional variance term actually appear in the bound, right? And I think this justifies why it's a good idea to actually find the feature representation that try to minimize this term, because then you get a tighter bound with if this term is small. Right? The rest of the term in the generalization bound is like, okay, it's the term that decay to zero with the number of sample and also the number of domain. Right? And after this work, there exists a long list of work that basically try to build more complicated model and using different principle to learn across multiple domain, right? And basically trying to solve domain generalization problem, right? To give you some example, there exists this domain invariant training of neural network. Basically, they look at sort of adversarial training approach, right? that trying to, basically the idea is type similar to minimizing the distributional variance, right? But using the adversarial training, right? You want to train a model to distinguish data from different domains as well, and then treat it as an adversarial training so that after you learn the predictive model, right, this discriminator model cannot distinguish data from different domains, right? People have also looked at the causal invariant prediction, right, by assuming that what remain constant across domain is the causal mechanism that generate the data, right? There's also invariant-based minimization, and I think DRO, which is also quite popular, right? Look at the worst case solution in a ball or epsilon ball around the empirical distribution, right? Now, I think that although there's a lot of, I think, work in this direction, right? Most of them, right, focus either on the average case solution, which is looking at the average accuracy across domain, or trying to look at the worst case solution, right? Finding the worst solution across all the domain, or you can also find the solution that is work best, well, on average, right? This probable domain generalization basically try to also argue that actually there exists no single objective that you should focus on. Actually, you could always find something in between the average case solution and worst case solution, right? Right. So the points that I want to make here is that all these approach, right, somehow reduce the problem into precise learning problem, because as soon as you focus, or as soon as you commit, or the learner commit to specific solution, right? I would call specific notion of generalization, either average case solution or worst case solution, then the problem becomes a precise learning, because the goal now is just to optimize the objective that you pick, right? And this is precisely what I'm trying to make, right? The point that I'm trying to make here is that all these approach that trying to solve a domain generalization problem, right? We can actually summarize it like this. So the precise learner, we have to deal with two sources of uncertainty, right? Data uncertainty and distribution uncertainty simultaneously, right? So I think the learner do that by first choose what is the right notion of generalization, right? And this can be translated into maybe picking specific distribution in the Pareto set. And then based on that choice, formulate the objective and then minimize that, that objective function to find the best solution, right? Now, the first problem is when you deal with distribution uncertainty, I argue that this is actually a decision-making problem, right? And it's a decision-making problem because it involves also subjective choice and the judgment of the learner. Whereas the data uncertainty, right, the way that the learner deal with data uncertainty is the statistical learning problem. Okay, and in most of the work that I discussed, this happens simultaneously. Right. Now the question is why is it not? Why is it a problem then? Right. I think this is a problem because from my perspective, right, whenever we deploy machine learning model or train machine learning model, right, I think we have something that is called, that I call actually institutional separation. And this is the term that I took from this paper by Mansky, right? And the problem with institutional separation is that the person, right, or the agent who actually train machine learning model is not going to be the one who actually deploy that model or actually use that model, right? And now if you allow the learner to commit to specific notion of generalization, right? That feel like, okay, it's kind of it feel wrong for me, at least, that, you know, as a learner, as a machine learner, for example, at DeepMind, or as an engineer at DeepMind, I know what the doctor who is going to use my model want, right? So I'm kind of making decision for the operator, right? So one of the example here is that you could imagine that the learner could be someone who work at a company, right? And then have access to the data, right? And then the goal is to train this machine learning model, right? And then you can imagine the operator of that model could be maybe doctor in the hospital, right? Or someone, let's say also policy maker or decision maker, right? Or whoever who might want to use a machine learning model, right? So and the standard model in machine learning assume that the learner have the capability or at least know what the operator want, right? What we actually want, right? In the end, I think this is my opinion, but I think what is the right way to do this is that, as a learner, right? If the learner have imprecision about the data distribution, right? The learner should be able to remain non-committal about specific choice about that distribution, right? This person should basically be able to remain sort of non-committal about the right choice or the right notion of generalization, right? And then let the operator of the model pick what is the right notion of generalization, right? And so this is the key message that I actually want to convey in this talk. And this is exactly what we try to achieve in this ICML 2022 paper, domain generalization via imprecise learning, right? And the idea is basically as follows, right? So we have an imprecise learner, right? And then we have, so here we assume that we have access to n domain, right? And we have, basically we don't observe the underlying distribution, but we observe data from different domain, let's say n domain in this case, right? And then we gonna treat a credo set that is generated by this distribution, right? Observed distribution as the representation of uncertainty by this imprecise learner. Right? Now the question is how should this imprecise learner learn, right, from this representation of uncertainty? Now you don't have just a single probability distribution, right, as a representation, but now you have a set of probability distribution. Right? So now we're going to assume that from these n probability distribution, we can form a risk profile, right? We call it a risk profile. And basically is represent the risk value of hypothesis across different domains, right? So here F is the hypothesis, right? And then the risk profile just tell us, okay, what is the risk value of this hypothesis across n domain? Yeah. Okay, and then we're gonna assume that we have now an aggregation function rho, right? And indexed by lambda, right? And this rho basically is gonna aggregate the risk profile into a single risk functional, right? And we have this parameter lambda that I'm gonna talk a bit more about in the next slide. But this lambda is kind of a free parameter or choice parameter that the operator, right, of the model can actually choose from, right? And that means that actually for a fixed value of lambda, right, we can basically learn from a hypothesis class by just minimizing this aggregated risk, right? So this, as soon as you know lambda, right, you know exactly how to solve the learning problem, basically by just minimizing the aggregated risk, right? And basically, okay, one thing I want to say is actually this lambda, you can think of it as a way to traverse, right? Way of traversing across a credo set, right? So if you pick specific value of lambda, then it gives you specific point in the credo set. Okay. That means that if you are a precise learner, you can start by choosing what is the right value of lambda, right? As a learner, you can say, okay, lambda should be 0. Then you choose that lambda, and then you just solve this precise learning problem. Okay. So because in this work, we don't want to do that, right? We want the learner to be able to remain imprecise or remain non-committal to this choice, right? So what we're gonna do is that we're gonna actually instead learn an augmented hypothesis, right? This is actually denoted by H, and then this hypothesis is parameterized by theta, which is a parameter of this model. And this hypothesis actually take in, well, okay, I think there's a typo, but I think this hypothesis actually take in not only X, so this should be X, right? And lambda, and then split out the prediction. So what happened here is that we add this lambda to the argument of this hypothesis so that at test time, the operator can decide what's the right value of lambda to pick, right? And ultimately, what we want is that if we specify the value of lambda to this augmented hypothesis, right? The optimal augmented hypothesis should give us the optimal solution, right? As if we know what the right lambda is. It's basically the hypothesis that minimizes this precise objective, right? So now the question is, basically, as I said before, this is basically a parameter that allows us to traverse the credo set, right? I kind of want to make this connection to also what happened in machine learning literature as well. I think we talk a lot. I think if you're familiar with LLM, we talk a lot about like fine tuning, prompting as well, right? And this lambda is kind of a way that you can prompt the the machine learning models, right? You can prompt, okay, this is the lambda that I want. Now give me the right prediction, right? So now you can change the prompt, right? I mean, let's say if you want different thing, you can change it to different values, right? So I think that may be a different way of understanding this, but let's keep it very simple, right? And in this work, we focus actually on specific aggregation, right? Which is conditional value at risk. And the reason we picked this one is also not only because it had been studied a lot in the literature, but also because it gives us a very nice interpretation in terms of different value of lambda here. We have an interpretation in terms of lambda, right? So for those who not familiar with this, what is conditional value at risk? So the conditional value at risk is basically if you look at the distribution of the risk, right? So this is the distribution, right? So the conditional value at risk gives you sort of the expected risk value, given that the risk value is above certain quanti, right? Lambda quanti, basically, right? And this is the value at risk, right? And then you identify the quanti and then take the average or expected value of the risk above this point, right? And this has a very nice interpretation because now actually you can interpret this lambda as a sort of the level of risk aversion, right? And already many work in machine learning already make use of this kind of interpretation in their work, right? Right. You can imagine, okay, if I pick lambda equal 1, then this gives you sort of the worst case solution, right? Correspond to specific maybe distribution in the credo set. And then if you pick lambda to 0, then this gives you the average case solution, right? So we in this work we focus only on this in this aggregation function, but in principle, I think we should be able to generalize this to any risk measure. Okay, so now the question is, because we don't want to commit to specific value of lambda, right? I think then the question is, how do we define the notion of optimalities of the hypothesis, right? And of course, one of the most natural choice of optimalities is this Pareto optimality. In this work, we call it C Pareto optimality. So we want to sort of find the models, right, in such a way that it will not be dominated by any hypothesis in the hypothesis space. And what I mean by dominate is basically exactly this one, right? So H theta dominate S theta prime if for all value of lambda, right? The aggregated risk of the S theta is smaller than or equal to H theta prime. And this inequality should be strict for at least one value of lambda, right? Yes, of course, I think this makes sense, right? But then the question is, how do we solve this, right? And we show that in the paper that you can actually compute a scalarized objective from this, right? So here we have infinite number of objective function to look at, but we show that if you pick Q, right, which is a probability distribution over lambda, and if Q has full support, then you get a single objective that recover the solution on the left-hand side, right? And this is easier to solve because now you just have one objective function, right? This is nice, but I think it doesn't really resolve one of the questions we have, right, from the beginning, because in the end, when we train the model, we don't want to commit to specific value of lambda, right? Also, we don't want to commit to specific distribution over lambda because that also defeat the original objective of our, right? I think then the question is, okay, can we use uniform distribution, right? I think before I learned about imprecise probability, I would say yes, we can use uniform. But after I learned a bit about imprecise probability, now I would say no. Because I think uniform distribution tell us that, so you cannot distinguish, right, between the lack of knowledge from like the knowledge of having sort of the belief across different value of lambda, right? And I think if you ask most of machine learning people, including myself, uniform will be a natural choice that people would use in this. One way to interpret this result is also that, as long as you pick Q that has full support, then you can solve the problem, right? You get the solution. But I think we don't want to do that. We want to sort of implement this notion of being imprecise about the right choice of lambda. And I think I will show that later in the experiment, that actually being imprecise in this case actually buy you something, right? And we kind of resolve this choice of Q by proposing, right, the gradient update in such a way that every update, right, the update will make C Pareto improvement, right? We pick the choice of Q in such a way that this update will always give us a Pareto improvement. And as soon as we cannot make any improvement, we stop, right? That's how we learn the model intuitively, right? And the algorithm that we propose is also similar to multiple gradient descent algorithm that is used in a multi-objective optimization, right? So let's look at how this idea of being precise by something for us or not, right? So in this experiment, right, we compare different approach, right? Mainly precise learning with imprecise learning method, right? And this is how we generate the data, right? And we generate the data from multiple domain, right? In each domain, we have about 250 training data and then 250 test data. And the sample size for each domain is 100, right? So now what I show here is the plot of the CVAR values, right, of the precise learning, or you can think of this as a ground truth. Why is it the ground truth? It's a ground truth in the sense that I assume, right? We assume here that the learner know the right value of lambda, right? So we have two values of lambda here. So the lambda of the learner and the lambda of the operator. So in this case, it gives us, so what happens if the learner know the right value of lambda for the operator, right? And this gives us sort of the ground truth CVA value across different value of lambda, right? So now we compare this to precise learning, right? Precise learning, the first precise learning approach is basically when the learner commit to specific value of lambda. In this case, the green one corresponds to lambda equals 0, right? And this red one corresponds to lambda equal 1, right? So what happened when the learner commit to lambda equals 0? You can see that as the operator, right, the lambda of the operator is close to 0, this model actually does quite well. But as soon as, there's some discrepancy between the lambda value of the operator and the learner, the model actually diverges quite quickly. It's the same with this model, right? Right. So I think the message here is that if you commit to something, it's good if that choice is the right choice, but it's bad if the choice is not the right choice, right? It's pretty clear, right? We also compare this to uniform distribution, right? The uniform distribution now give us the same kind of behavior as in the commit to lambda equal 1, right? So it doesn't help, to just impose uniform distribution over lambda, right? Still have this problem. Now, the red one is the solution that we propose, right? As you can see, we don't commit to any lambda. We implement this imprecise learning. And as you can see, we kind of maintain sort of the CVA value that is close to the ground truth, whatever the value of lambda for the operator is, right? So this demonstrates the benefit of, being imprecise in learning when there's a institutional separation between learner and the operator. And I also want to highlight this work. I think Michele already mentioned this work, very, very beautiful work. Also, that also explore similar idea, but he actually looked at the learning theory side. I highly recommend everyone to look at this paper. I really enjoy reading this paper. So yes. And okay, to sort of to wrap up, right? I want to sort of point out that this OOD generalization problem is actually an instance of the learning with ambiguity, right? We have the ambiguity in the sense that we don't really know what is the right notion of generalization we should pick, whether it should be average case or it should be worst case, right? And in that case, what we propose here is that we should remain imprecise whenever we have this ambiguity, right? And this kind of problem actually quite common in machine learning these days because of the additional constraint or additional demand we want from machine learning models, right? For example, we want the model to be fair. We want the model to be interpretable. We want the model to be robust. We want the model to be trustworthy and also private, right? But, fairness, interpretability, robustness, trustworthiness, and privacy, these are all subjective, right? Maybe the model that is fair for one person is actually unfair for the other. Model that is private for one person may be non-private for the other, right? So this subjectivity or requirement actually create a problem for us. I think create ambiguity for the learner because I think what happened in the community right now is that we assume that the learner know what is fair. The learner know what is private or the level of privacy that the user want, right? And I think the problem is because I think in the real world, we have this institutional separation, right? Actually, you can already observe this trend because it actually changed the training pipeline of the machine learning pipeline, right? We have foundation models, so now we split the training process into two parts, a pre-training part and fine-tuning part, right? because we realized that there's institutional separation between the learner who might have more resource and then the operator will actually have fewer resources. Right? It's also happened in LLM alignment as well. Right? And I think for me, this demand actually sort of a new model for machine learning. I think a few models come to mind. For example, principal agent models, heavily studied in economics, and also in complete information game. Right, it's heavily also heavily studied in economics. And I think the point that I want to make in this slide is that we focus a lot on these two axes, right, in machine learning. We have a lot of data. We're trying to get more and more data to build better and better model. But then we often neglect that we also have to deal with choices, right, that come from heterogeneity in the population. Right. And I want to highlight some of the recent work and future direction that we look at. Next week, we're gonna present this work, Credo to Sample Test of Epistemic Uncertainty at AI Stack 2025, which is gonna take place in Phuket, Thailand. Not my hometown, but very close to my hometown. Yes, and we also recently worked on the problem of elicitation of imprecise forecasts. Right, because I think we believe that this is actually also relevant to OOD generalization and one way of overcoming the institutional separation. And this work is highly inspired by work by Christian and Bob Williamson on scoring rule and calibration for imprecise probability. So if you have time, I also highly recommend you check this paper out. I really enjoyed this paper. So, and we're also looking at different topics with our group member. So if you're interested in collaborating, I would be happy if you can reach out to us. So to conclude, right, I think in this talk, the point that I'm trying to make is classical generalization can be achieved via precise learning, such as ERM, right? And previous work, right, in domain generalization, covariate and domain generalization address the distribution shift by still reducing the problem to precise learning, right? And what we're trying to argue is that OOD generalization involves both decision-making and statistical learning problem. So it cannot actually be reduced to precise learning because of the institutional separation, right? We cannot say the learner know everything about the operator of the models, right? And imprecise learning will enable the learner to be less committed to specific notion of generalization and will allow the operator to make informed decision when they deploy that machine learning models. And these are the reference of the paper that I would highly recommend you to look at if you're interested in, especially the last one, very, very beautiful paper. And these are the people which in my group. So special thank go to them as well. And also special thank go to Anurag and Alan who actually worked on this project. Alan is already leaving our group to NTU. So he gonna start his own group and he gonna work heavily on imprecise probabilities, right? So reach out to him as well if you want to collaborate. And in September, we will have Julian Roderman joining our group as a postdoc. And that's actually bringing me to the end of my presentation. Thank you.